Alright, and we're here to do a couple of examples from Power Standards Quiz 31, 32, 33, and 34. I got an example from each of those in that order. So we have Power Standards Quiz 31 first. We have an expression on the screen here, 4g to the fourth, h to the fourth, that whole quantity to the third power, and we are asked to simplify this expression. So if we look at this, what's in the parentheses? What's inside the parentheses, the 4g to the fourth, h to the fourth, this whole expression is to the third power. So what this means, if we were to write this out, is it means 4g to the fourth, h to the fourth, times 4g to the fourth, h to the fourth, times 4g to the fourth, h to the fourth. We're multiplying what's inside the parentheses by itself 3 times because that is the exponent. So we have this long sentence here. This is written kind of expanded out a little bit. We have 3 4g h to the fourths. And if we have this, we can simplify this now by combining the g's and the h's with their exponents by adding those exponents. But first we see we have a 4 and a 4 and a 4, and since we're multiplying all these things together, if we multiply 4, 4, and 4 together, we get 64. If we have g to the fourth times g to the fourth times g to the fourth, that would be g to the 12th because we would have 12 g's. This right here means g times g times g times g, as does this and as does this, and if we expanded that out, we would have 12 g's being multiplied together, which in short can be represented as g to the 12th. Then we have h to the fourth, and the same thing with the h to the fourth. We have 4h's here, 4h's here, 4h's here, all being multiplied together. So that, in short, is h to the 12th. And once we have this, there's nothing else that we can combine together because none of them have the same bases. So we have 64, g to the 12th, h to the 12th, and this is your simplified version of this expression here. Next example, we have a couple more expressions in parentheses, and the parentheses are kind of here as a distraction of sorts because all that we're doing here is multiplying these things together. All this says is a to the fifth times b to the third times a to the third times b to the third. So I can write this expression here as this. I'm just multiplying these four things together, these four factors together. A to the fifth, b to the third, a to the third, b to the third, all being multiplied together. And when we're multiplying things together, we combine the factors with like bases, and we add their exponents. So we have a to the fifth here and a to the third. That can be written as a to the eighth, and the reason why is because if we expand that out, we will have 5 a's here from a to the fifth, 3 a's here from a to the third, and notice we have 3 b's in the middle from this b to the third, and these 3 b's here from b to the third. So this is expanded out now. This right here is exactly what this sentence is saying. A times A times A times A times A 5 times, B times B times B from B to the third, A times A times A from A to the third, and B times B times B from B to the third. And if we count these together, we'll notice that we have 8 A's, which is why we have 5 plus 3. So you have A to the 8th, B to the 6th. Why B to the 6th? Because there are 6 B's. And that's where that comes from with the 3 plus 3. So your simplified version of this expression is a to the 6th, a to the 8th, b to the 6th. Another example, simplify the expression. We're going to write it without negative exponents. Negative exponents are a nasty looking thing, and we want to get rid of them. And it's not just as simple as getting rid of or erasing the negative sign in front of the numbers. We need to do some mathematical manipulations, and this is as easy as moving the power with the negative exponent to the denominator or the numerator of the fraction. So when I look at this expression here and it says write it without negative exponents, I have to identify the things that have negative exponents. The first thing I see that has a negative exponent is m. M has a negative exponent because it's m to the negative third. The 36 does not have a negative exponent. The m does. The n does not have a negative exponent. It has a positive exponent of 5, so I'm not going to worry about that. The 2 does not have a negative exponent. This m does not have a negative exponent. This n does have a negative exponent of negative 2, and this p does have a negative exponent of negative 4. So what I'm going to do is take those powers, those bases with negative exponents, and move them to the opposite side of the fraction that they are on. So if they're in the denominator, they will move to the numerator, and if they are in the numerator, they will move to the denominator. So what that will look like is this. The 36 stays put. The 36 does not have a negative exponent, so I don't have to move it. Notice there's an n squared here. And the reason there's an n squared here is because there was an n to the negative second in the denominator. So I want to take this power and move it to the numerator, which makes the exponent positive. Then I have n to the fifth. This n to the fifth right here was from the original expression, n to the fifth. I don't have to move that because it does not have a negative exponent, and that just accidentally showed up there, so we'll talk about that in a minute. P to the fourth comes from right here. P to the fourth is from this p to the negative fourth. So I move this p to the numerator, and the exponent becomes positive. In the denominator, we have this 2 from right here in the original expression. Don't need to move that. We have the m from right here, and then we have m to the third. This m to the third comes from this m to the negative third that was in the original expression. Move it to the denominator, and the exponent becomes positive. Now we can talk about this. The 18, from simplifying this expression now, the 18 comes from 36 divided by 2. 36 over 2 can be simplified to 18, 18 over 1. So that's where the 18 comes from. N to the seventh, well, we have n squared times n to the fifth. Add these two exponents together, because we have 7 n's in the numerator, we get n to the seventh. P to the fourth, there's no other p's to combine that with in the numerator, so we leave it as p to the fourth. And then m to the fourth comes from the m times the 3 m's here. If we wrote this out, we would have 4 m's. We have 1 m right here, and then times m, times m, times m, which is m to the fourth. And the 2 is gone because that was reduced when we did 36 divided by 2 as 18. So this is our simplified version without negative exponents. Notice there's no negative exponents in this expression. And the last one, simplify the expression. We're going to write it again without negative exponents. And last time, with the last example we just did, we talked about it being a fraction and moving it from the numerator to the denominator. Notice this is not a fraction. So I'm going to make it a fraction. And how we make any term or expression into a fraction is to take that term or expression and put it over 1. And now I'm in a position to where I can move things to the denominator, because now a denominator, at least visibly, exists. So I have to identify the things with negative exponents. That's the a, because that is negative 7, and the c, because that has a negative 9. So all I'm going to do is take this a to the negative 7th, move it to the denominator. I'm going to take the c to the negative 9th, move it to the denominator. I'm going to leave the 6, and I'm going to leave the b to the 8th. Why? Because they do not have negative exponents. So if I move those things with the negative exponents to the denominator, notice our 6 and our b to the 8th still in the numerator, and the a to the 7th and the c to the 9th have now moved to the denominator, and the exponents have become positive. And now there's no other things with like bases here, so we leave our answer as it appears right there.